All right, so we're talking related rates today, and came across this quote from Nelson Mandela. Some good stuff right there. Anybody should know about dealing with what we think is impossible, as Mr. Mandela. So, yeah, if you don't know the life story of Nelson Mandela, you need to check that one out. Some good stuff right there. So, I think you've had it hard. You don't even know. All right, let's talk related rates. And where am I? Here am I. Okay, so related rates. Basically, we're talking the derivative with respect to time. So all these different things are going to be doing d over dt for everything. So sometimes you might end up with having dy over dt and dx over dt, or dr over dt and dA over dt, or dv over dt, and all sorts of different d something over dt, but it's going to be over dt. And then super important are going to be mind your units. Okay. Very, very important on all these is to make sure you pay attention to your units, because these are all going to be talking about some sort of thing that's really like it might be a manufactured scenario, but these are things that could actually happen. So, a lot of the time with these ones. Now we're going to start off with something basic, okay? Let's just say we have a function, y equals 2x squared plus 1. It's just hey, this is a happy parabola with a y-intercept of 1, okay? Basically, the idea is you have this particle that's moving along the parabola, and it's all happy as can be, and it's moving so that way dx over dt is 2 centimeters per second. So what directions are going to be moving? To the right or to the left? It's going to be moving to the right because dx over dt is positive. Remember, positive means to the right, positive velocity. Derivative means velocity, so positive dx over dt means to the right. Okay, and then to the left means negative dx over dt. And just imagine this is you. Okay, so imagine you are this little dot. Okay, and you are cruising around happy as can be on your two-dimensional world that really acts more like a one-dimensional world. So you can think of it as basically a 1.5-dimensional world. It's this is you, okay, and you're moving to the right. Well, what direction? If you're right here at x equals -1, not only are you moving to the right, but what other direction are you moving? You're also moving downwards, because to go to the right and stay on your world, you're going to have to go downwards. And so when we go through these, you're going to see something happen that for some of these, like when we look at x equals -1, our answer better be negative if we're finding dy over dt. And over here on x equals 1, now if we're over here and we're moving to the right, well, we're still moving to the right, but now we're going to be moving upwards. So it means dy over dt should be positive. That's right. And then what about at x equals 0? Well, think about it. Okay, we'll get to it. All right. Now, so in all of these, what we're asked to find is we're going to find dy over dt at a point. So there's some things that you're going to need to know, okay, with all of these. You're going to need an equation, okay? For all this stuff, you're going to need some sort of equation. You might have to make that equation. You're going to need some information given to you about x or y or something, okay? So you're going to have other information that's going to be given to you. So you have to be able to sort through those different things. Dx over dt in this case is given to you. X is given to you. So let's just think about this one all by itself, this instant. And we're going to find dy over dt. This is all the information that we need. We need our equation and we have our givens. And this is our asked for. We have to find our asked for. So, well, let's just start off with y equals 2x squared plus 1. Well, if we want to find dy over dt, well, then that means we have to take the derivative with respect to time. So we're going to do d over dt to both sides. Well, the right side is going to be dy over dt. That's pretty obvious. The left side now, we're going to have 4x times, that's right, dx over dt. So we need that. Plus nothing. So, okay. We want to find dy over dt. We know that at this instant, x is -1. So we have 4 times negative 1. dx over dt is 2 centimeters per second. And so all this comes out to be negative 8 centimeters per second is the idea. And so our dy over dt, like I said, it has, well, negative. I've said negative. I just didn't write the negative thing. So it has to be negative because it's going downwards. Remember on the parabola, look back at our parabola. At this point, not only are we going right, but we're also going down. And so that's why we end up with dy over dt equals negative 8. Okay. Well, dy over dt is going to be, the function is going to be the same no matter what. So 4x dx over dt. That's going to be the same throughout this. So there's no reason to go through and find the derivative multiple times for the same problem. But, and then also in each one of these cases, dx over dt is 2. So really we could call this 8x because 2 times 4 is 8. So 8x. So dy over dt is going to be 8x for these. And so here x is 0, meaning dy over dt would be 0. And then dy over dt would be 8. But 0 or 8 what's? Speeds? No, it's going to be centimeters per second. Again, pay attention to the unit. So you can see what's going on. Here, the particle is moving downwards. Here, it's moving upwards. Here, it is moving neither downwards nor upwards. It comes to a full and complete stop at that point. That's when it turns around. That's what we call the minimum. And if you look at our parabola, you can see where that happens. All right, so this is a kind of a basic one that doesn't fit anything. So let's talk about something a little bit more, well, tangible. Okay. And so now we've got a spherical balloon that's inflating at a rate of 800 cubic centimeters per minute. So now we're told something. We have to identify what that something is. If we're talking about cubic centimeters, what are we talking about? We're talking about volume. And since it says per minute, we're talking about the derivative with respect to time. So what we would do is we would call this dv over dt. That's what this is. This is dv over dt. And so if we're taking the derivative with respect to time, then what formula should we use? Well, we need the volume formula is what we're going to need. So you need a spherical balloon. So what's the volume for a spherical balloon? Well, that's 4/3 pi r squared, or pi r cubed, I'm sorry. This is the volume of a sphere. Now it says, how fast is the radius increasing? How fast is the radius? Okay, that's the key. That phrase tells us we got to find what? We have to find dr over dt. How fast means a rate, that's d over dt, of our thing. Our thing is radius, so dr over dt. Increasing at the instant when r equals 330 centimeters. So this thing right here, and this is what happens. If you think about a balloon, if you're blowing up at a balloon, even if it's just, say, you're using a pump or whatever, there's one instant where the radius is 30 centimeters, but right before it wasn't, right after it wasn't. But at that instant, at that snapshot in time, if we were just to fire off a speedometer at the balloon, we could be able to measure this sort of thing at that instant. So this is stuff we're going to use. We're going to find dr over dt when r equals 30. So all right, so now what we do, we have this. Again, we've got to use dv over dt. We got to find dr over dt. So both of these things are screaming at you to do what to that function? Screaming at you to take the derivative with respect to time, because d over dt. All the times before, we've been doing d over dx, sometimes with other letters, but mostly it's been with x. Now it's going to be about t. Related rates are all about t. So what we do is we end up with dv over dt, and that's going to equal 4 pi r squared, which is the surface area of the sphere, times what? dr over dt, because of the chain rule. Okay, and r isn't t, so you can think of it because of implicit differentiation, or however you want to think about it. I don't care, but every time you have if this variable doesn't match that variable, you need the d thing in the dt. Okay, so dv over dt was 800. 4 is, well, 4. Pi is pi. R is 30. And dr over dt, well, that's what we're trying to find. And so we are here, okay? 30 squared is 900. 900 times 4 is 3,600. So we're going to divide both sides by 3,600 pi. So 3,600 pi. You can reduce that, of course. Again, if you're doing a free response question, you don't need to worry about reducing. You can just leave it alone. But these questions do appear in multiple choice questions as well. So be ready to reduce. 8 over 36, both are factors of 4 or multiples of 4. So we end up with 2 over 9 pi, because that pi is still down there. And again, this is r. Well, how are we going to tell about the units? We're going to go back up here. It says centimeters cubed per minute. This is at centimeters. dr over dt. So a few things. Lengths, r, radiuses, lengths, heights, these are going to be measured in centimeters, feet, inches, miles, okay, all to the power of 1. Area, squared. Volume, cubed. This is a length, so centimeters per minute was. And so you use this information up here to figure out what's going on. All right, so let's take a look at a possible sort of problem that you could come across on the AT test, especially if you were to time travel back to the year 2002 and take the test. So if we were to do that, and all right, so you go back in time to the year 2002, and you're taking a look at this test right here, and we get this cone. It's a cone. Sometimes, notice sometimes here, they will give you the volume formula. Not always, so just be on the lookout for that. All right, so they give you the volume formula. The container has a shape of an open, bright, circular cone. That means that there's nothing on top. Okay, as shown in the figure above, the height of the container is 10 centimeters, and the diameter is 10 centimeters. Water in the container is evaporating because it's open. So the depth h is changing at a constant rate of negative 3/10 centimeters per hour. So that's what h is changing. So what would we, it says h is changing at a rate of, which means that this is called dh over dt. So let's write that down. dh over dt equals negative 3 over 10. And if dh over dt is negative, that means h is decreasing. And if h is decreasing, that means the water level is going down. So if the water level is going down, and we want to find the rate of change of the volume, okay, think about this. If the volume radius is, the height's going down, what's going to happen to the volume? That's also going to be negative. So, at the end, your answer should be negative, is what should happen. Okay, and we look back at our problem before on the last one. Not only we know that was inflating, but it said how fast is radius increasing. That tells us our answer better be positive. In this case, we know from thinking about it that our answer has to be negative for part B anyways. All right, this is negative 3/10 centimeters per hour. Okay, if you're thinking that the phrase, that's really small. Yes, it is, but it's evaporation. Evaporation takes a long time. Okay, so we got that right there. And then we want to know, hey, we're also told that V equals 1/3 pi r squared h. So it'd just be helpful for you just to know this, okay? Now, the problem with this, and if we're thinking about our cone, okay, so imagine your cone right here. Okay, and then you have your liquid in here, okay? This liquid, okay, as we already know h is changing, but as h goes down, that means then that our radius is also shrinking. So even though it says that the diameter across the top was 10 centimeters, which then means across the top has a radius of 5 centimeters, and our height of the whole cone is 10 centimeters, is our radius always 5? No. As the water level shrinks, the cone gets smaller. The radius shrinks. Is our height always, is the height of the water always 10? No, the height of the water is not always 10 because the water is shrinking, it's evaporating. And what shape is the water always going to be in, though? The water is always going to be in the shape of a cone. So that means this still applies to the water. Okay. Well, the question that they ask on part A says find V, the volume of the V when H equals 5 centimeters. So 5 centimeters means H would be right here. Means H equals 5 at this instant. Okay, because there's one instant where as the water evaporates, there's one instant when the height is 5 centimeters. Cool, that's great news. But what's our radius going to be? Okay, well, maybe it'll be, so our radius of the original cone was 5. Okay, now if we're trying to find the volume of this, is this going to be half of the total volume? No, it's not. Okay, if it were a cylinder, sure, that would happen. But it's not, because the pointy part is smaller than the other part.
Mom wants to know if you're comfortable with Joshua having a lemon ball. The lemon head.
Oh, as long as the lemon heads or lemon balls?
The lemon heads.
Lemon heads are okay.
Okay.
All right. So, okay. Lost my train of thought. Okay. So this volume up here is makes up more than that volume. That the volume of the air is bigger than the volume of that liquid. So, all right. So we just can't find the volume of the whole thing and cut that in half. So instead, though, we got to come up with some sort of function that's going to relate this. We know what H is. We don't know what R is. Now, so you might look at this and, well, if half of the height is 5, well, shouldn't the radius be half of that 5 right there, make it 2.5? And you would be correct. And the reason for that is because of what we call similar triangles. That's how this works out. So imagine we get this triangle, okay? And so this is little r. We know that that's 5. Okay? This triangle, this little triangle of the water, is proportional to the big triangle. The big triangle has a height of 10, but a smaller height for the little one. And so you can set up the ratio, and you can say, okay, we say 5 over 10 equals R over H. R over H. Because, so the short leg over the long leg equals the short leg over the long leg. That's how similar triangles work, which then means that R is actually 1/2 of H. And so we can look at this like, oh yeah, R is half of H. R is half of H. We said 2.5, that's half of 5. So cool. So if we want to know the volume when H equals 5, then what we could do is actually we could take this now and we could substitute that in for our R. So we'd actually have V equals 1/3 pi. This is R, 1/2 H squared times H. Okay, if we square a half, we get a quarter. Quarter times a third is 1/12. So we have 1/12 pi H cubed. And so this would be our volume formula. And so when H equals 5, then we'd end up with V equals 125 over 12 pi. Because 5 cubed is 125. And you can leave it like that. And that's going to be volume. And we're going back to our measurements. It's centimeters. So volume is centimeters cubed. Neato. Okay. All right. And now, the interesting part to what we're talking about is we want to find the rate of change of the volume. So we're talking about rate of change of the volume. Cool. So that means we want rate of change of volume. This means d over dt, okay, of volume. Of means parentheses. Volume means v. We want dv over dt is what we want to find. And so what you got to do is you got to learn how to read it. Look for the key phrases. Rate of change means d over dt of our volume, dv over dt. So then when we come through, we take a look here at this problem, which said we have v, 3 times the 12th is 1/4 pi h squared times dh over dt. That's h is not t. Implicit differentiation, chain rule, whatever you want to call it. And so we want to find the rate of change when h equals 5 with respect to time. With respect to time means dt. So that means we'd have v would be 1/4 pi 5 squared, or dv over dt. I'm sorry, this is dv over dt. Yeah, dv over dt equals dh over dt, which was -3/10. So I'm going to put that back here. So we have -3/10. So we end up with dv over dt, which would end up being 5 squared is 25 times -3 is -75. And then we have pi, and then we have 4 times 10 is 40. And this will be centimeters cubed per hour. Centimeters cubed because we're volume. And then, yeah. Of course, you can reduce that. I mean, 5 goes into both of those. So you end up with, what, 15 over 8? Yeah. So we end up with -15 pi over 8 centimeters cubed per hour. But this was a free response question. So you could have just left it at 75 pi over 40, 15 pi over 8. Don't forget the pi. It's important too. It's a number 2. Okay. And again, right here, so indicate the units of measure. Indicate the units of measure. Really, really important. Okay. Show that the rate of change of the volume of the water in the container due to evaporation is directly proportional to exposed surface area of the water. So you got to think now, which part do I need? Does that mean I need to know the surface area of the cone? No, you don't need the surface area of the cone. We want the surface area of the water. But the water is a cone, Mr. Brandt. Yeah, but what is exposed? He wants the exposed surface area. What shape of the water is exposed? And it's just that circle on top. So the exposed shape of that is going to be pi r squared. That's the area of it, is pi r squared. Okay, but then you're thinking, okay, but nice, but what is r squared in this? Remember what's r? Okay, well, we already did r. R was 1/2 h. So this means we end up with pi times 1/2 h squared. Okay, this is our area of our water. This is an exposed surface area. So then that's going to be pi over 4 h squared. This is a. Okay, that's now it says the rate of change of the volume of the water. What's the rate of change of volume of water? dv over dt. So that means dv over dt, which we already said was, if you look right here, 1/4 pi h squared. And wait a minute. That's what that is. 1/4 pi h squared. So 1/4 pi h squared. That's what that is. Times dh over dt. Oh, wait a minute. That means that this is a times dh over dt, which was -3/10. Remember? That's what they started off with. So we want to come back, okay? Show that the rate of change of the volume of the water in the container, dv over dt, is directly proportional. Means you multiply something by a constant to the exposed surface area of the water, which was a circle, or a, if we will. What is a constant of proportionality? So directly proportional means you take the thing and you multiply by a constant. This is a constant right here. K is -3/10. That's what we're talking about. This is our constant of proportionality. Okay, so I just want to show you some things of how this looks, and try these out. Okay, we're going to do 12 of them. I kind of did one of them already. Well, 2 of them already for you. So 1.5. So try the rest of them. Let me know what you think. If there's anything that you want to get cleared up, any specific things. So please let me know, and I'll try to help you out.